Hey everyone, welcome back to Take You Forward. Today we will be solving the problem distinct subsequences. Again, it is a part of DP on strings. Now, till now, whatever problem we have done, we have seen that it uses the concept of LCS, right? But now we will be moving on to a concept which is something like string matching on DP on strings, where we generally do something similar to matching, and we will be doing three problems, and all of these three problems will be lead code hard version. Yes, all of these three problems will be lead code hard, and I can guarantee you that after this, DP on strings will look very simple to you. So what is the problem? It states distinct subsequences. Okay, so the first problem states you're given a string, and what is the string? BABG, and you're given another string bag. Okay, so you have to tell me how many times does the string 2 appears in the string 1. For an example, I can say BA, or if I use some other colors, BA, B, then G, and then BAG. So this, in this entire string, the yellow color is the string S2. So that's one occurrence. Similarly, if I try to write BA, this, if I take these three, there'll be another occurrence of bag, correct? Similarly, if I take something like BAG, there will be another occurrence, correct? Similarly, if I take BAG, there will be another occurrence, right? So what I can say is, listen, in total there will be five occurrences. Yes, in total there will be five occurrences of the string S2 in the string S1. You can call it as S1. The question is very simple. Given two strings, yes, given two strings, tell me the number of times the string 2 appears in string 1. That is a very simple question given to you. And how do you solve this? Obviously, we have to apply something like recursion. Now, why do we apply recursion and why not simple matching? Because what I can say is, if I have a bag, like, how do I approach this problem? My generic point of view will be, straight away let's take a bag and let's try to compare. Okay, B gets compared, A gets compared, next G gets compared over here. So that will be one occurrence. But you could have said, I will not compare this G, and I'll compare this G with this G. That be another occurrence. Similarly, you can say, I'll not compare this B with this B. Instead of that, I'll compare this B and this B. So you're saying that you have to follow different methodologies of comparing. Yes, I repeat, you have to follow different methods of comparing. Like, there can be multiple ways of comparing. If I ask you different methods of comparing, so it's kind of trying all ways. It's kind of trying all ways. So, whenever we try all ways, what comes to our brain? Obviously, it's recursion, right? Because that's the only way. When we say that, okay, we're going to try this way, and we take all the answers. That is what recursion is. You basically try and this way, and you sum up all the ways, right? So what is the question stating? It states, count the number of ways. Back to the recursion classes, lecture 6 and lecture 7 in recursion. Whenever there is something like count and ways, what do you think? Let's write down the pattern. It's generally a function, which is the recursive function. The base case tends to return 1 or tends to return 0, because you're counting the ways, and you call all the functions and you add up them and you return. That is what you do whenever the problem is count ways. Remember this? Whenever the problem is count ways, you write a function. You know the base case has to return 1 or has to return 0. And then you try out, this is one of the possible ways. This is one of the possible ways. And if there are other ways, you try out. And you add up all the states and you return. That's the generic way. And we have learned that in the lecture 6 and lecture 7 of the recursion playlist. But now the question arises, how to write the recurrence? Yes, how to write the recurrence? That's the plain and straightforward question. How do I write the recurrence? Okay, So what did I tell you in terms of strings? Over here, how many strings we have? We definitely have two strings, and whenever there are two strings, I've told you clearly that we are going to use two parameters. One parameter will be I, which represents the index in S1. The another parameter will be J, which represents the index in S2. So I can say the first step of writing the recurrence is very simple. Express, yes, I repeat, express everything in terms of in terms of I, which is the first string, and J, right? Or the second thing, explore all possibilities. And the third thing is count always. So return the summation of all possibilities. Return the summation of all possibilities. And I can say the fourth step is very simple. Write down the base case. That is something which we always do. You can call it as a step or you cannot. So if you do all these steps, I think we will be pretty much done. So what I do initially is I write f of ij as usual, and I'll keep the base case for the future. But as of now, I will try to write I and j is what we will try to write. Let's analyze what does I and j actually means. So what are the strings given? The strings given are BAP and this one, right? So let's quickly write down the strings. String S1 is BAP and string S2 is back. Okay. So when I say I and j, we know initially I is going to start over here, and we know initially j is going to start over here. Let's assume the length of the string S1 is n. Assume the length of the string S2 is m. We definitely know this. And we know one thing, this is nothing but n minus 1 and m minus 1, right? So what you're basically saying when you're starting off with something like f of n minus 1 and m minus 1 is the start call. What do you mean by this? What does this mean? Let's write that down. This means number of distinct subsequences between of, or you can say of, string S2 from 0 to, this is I, this is j, 0 to j in string S1, 0 to I, which means let's go back, which means you're saying this is, so number of subsequences of bag in this entire string. If I was over here and j was over here, the number of subsequences of bag in this particular string, because I is here, so I basically signifies that this much is the string. Got it? So that is what we are writing. F of ij, number of subsequences from 0 to j, like this is the string S2, in the string only from 0 to I. That is what it means. I hope you have understood the definition of f of ij. What are we trying to explain by f of ij? Okay, next. So we have written this and we have understood in terms of I and j. It is basically the string from, this is string S1 and the string S2 is 0 to j. That is what it means. And you have to give me the answer for that, right? So what is the next question? Explore all possibilities. Okay, so let's come back to this example of this S1 and this back. Okay, now assume this G is matching with this G. Assume it is matching. So you can be like, hey Striver, they're matching. So this can be the G, because for this G, I'm looking for a G in S1. Let's understand what are we trying to do. Let's understand this. What am I trying to do? I'm trying to figure this bag out. How many times does this bag occur over here? For that, what I'm trying to do is I'm taking this G and I'm saying, okay, this is the G, this is the G. Where's the A? This is the A. Where's the B? This is the B. So I'll get one occurrence. But what I could have also done is, I could have said, okay, I'll not take this G. I'll take this G. Then I'll take this A. Then I'll take this B. Perfect. That's one more occurrence. Or what I could have said is, let's take this G, but let's not take this A. Take this A, okay, and take this B. Again, perfect. Or what I could have said is, let's take this G, let's take this A, let's take this A, but don't take this B, take this B. So that's another one. Or you could have said, let's take this G, let's take this A, let's take this B, right? So what am I getting? What am I getting? If this is the G, I can take it. That's for sure because they are matching. I'll take it and now I'll look for BA. I'll look for BA in this portion. I'll take it and I'll look for BA in this portion. If they're matching, I'll take it and I'll look for BA in this portion. That is something which I'm sure. So if they're matching, I know one thing I'll do. So let's write that as of now and then we can think of other things. If they're matching, which is I is equal to S2 of J. If they're matching, I know one thing for sure. The string, the bag will reduce to BA. So that will be J minus 1. And you have matched someone. So this will also reduce. This is something which will happen to F. But, what does this mean? This again means you're saying this G matches with this G. So you're reducing the string to this and BA. But what if I say, hey, I'm not interested to take this G. I want someone else as G. So probably this one. So I'll say, okay, let's not match it. And let's keep the bag as it is. I'm not matching G. I am not matching G. Let's reduce it. Okay. So over here, let's find bag. Let's not match this G with this G. Let's take the entire stuff and match it over here. Can I do that? I'll be like, yes. Why? Because I'm looking for another occurrence of G. Because I'm not satisfied with this occurrence. Or I want someone else to be the G. So I'll be like, okay, I'll not take this G, but I'll try to figure out this entire portion. So this still stays the entire string, but I reduce this, saying that this G will not be accepted. Perfect. So I'll be like, fine. I can say, I'll reduce this first string, because this is not the G that I'm looking for. I'll keep the next string as bag only. I'll keep it as bag only, but I'll reduce it. I'll look for somewhere else. I'll look for the G somewhere else in the reduced string. So I think I can do this. And if I do this, eventually this G probably will match over here. But what if this G, because now, what if, just assume you came to a case where your I is here on A and your J is here. So you're like, A is not matching with G. There's no other way. You have to reduce it. It will get reduced and this will be the bag. You will look for G in the reduced string because this A is not matching with this G. There is no way in which you can match this G with this A. So you don't have any other option instead of reducing the string and saying let's find bag. Again, you'll not find B. So you'll again reduce the string and you'll try to find. And then you'll find G and G. So you have to reduce the string. You have to reduce the string in order to do the search. So I can say, okay, what if they're not matching? Because that might be a case in future. So if that's the case, I'll be like, I will reduce the first string and I'll still keep on searching. Okay, makes sense. So I've understood if they're matching, there can be two states. One is this, one is this. If they are not matching, then I'll reduce and look for somewhere else. So these are two different states. So can I say, I will either return this guy as the answer if they're matching, or I'll either return this guy. Perfect. Either this or either this, and that looks absolutely perfect. Now, so have I explored all the possibilities? I have indeed explored all the possibilities. Have I written the summation because it was count ways? I have. Base case, what is the problem? Problem is count ways. The base case has to return 1, has to return 0. There's no other way. Okay. So when will the base case return 1 actually, and when will it return 0 is my question to you. So can I say if I'm matching, what will happen? Ask yourself what will happen. Base case is asking yourself. Base case is ask yourself what will happen. Okay, let's ask. I'm matching. Okay, so I was like, what was it? Bab. Okay, and it was like back. What if there is a case where I'm still looking for B, and my pointer came out somewhere here, which is a negative index, which is definitely a negative index. So my pointer came across to a negative index, I can say. What if this happens? So if because if I was over here, then I could have matched this P, right? But if I'm standing here and I still have some portion of the second string remaining, this means I still have some portion of the die remaining. Thereby, I could not figure this B out and the string was exhausted. That's one of the base cases. Or I can say, yes, or I can say, I might end up coming to -1 on J, which means I actually have matched everyone. Which means I actually have matched everyone. And I think that's the case that I'm looking for. Because when do I return 1 is my question. When do I return 1 is my question. Can I say if all characters, yes, can I say if all characters of S2 match, then I return 1? I'll be like, yeah, that makes sense. So can I say the first base case is very simple. If I have matched all characters of the string S2, there's no thinking. Go across and return 1. But if this did not happen and I exhaust the first string so there is still matching to be done on the J counterpart. There is still some matching to be done on J counterpart. So I will go across and return a 0. That's it. That's how you write the base cases. As simple as it could have got. So we have written the recursion, right? And how many states are there? There are definitely 2 states. And I know the time complexity of this recursion, if I ask you, will go exponential. Assuming you're doing all type of comparisons, there can be a lot of comparisons. Somewhere near about 2 to the power n will be the number of subsequences of string S1, because those are the number of subsequences that you can generate if the string is of length n, and 2 to the power m of the string S2. So there will be matchings on them. So it will go exponential, you can call it in an interview. And the space complexity, if you're trying to go the auxiliary stack space way, it will go up to be go of n plus m, assuming you do simultaneous matches. So obviously the time complexity and space complexity is something which I'm not super happy with. I need to do it better. So I know one thing for sure, I can optimize this due to overlapping subproblems. Yes. Due to overlapping subproblems, you can try out drawing the recursion tree and you will see overlapping subproblems. And I am not drawing it because this is the 30-second lecture of the dynamic programming series and I have been telling this all over overlapping subproblems. So there is no way I'm doing that. Okay, so what do you do? A very simple memorization. And how do you memorize? What are the changing parameters? I, J, how much is I? N, how much is J? M, so N cross M dp, yeah? How do you do this? Right before returning, dp of ij equal to dp of ij equal to, and over here you write if dp of ij not equal to -1, return dp of ij, that's it. And if you write this, your memoization solution is indeed ready. And what is the time complexity of this? Obviously, the number of states, space complexity will be the number of states, the DPR that you're using, and BGO of n plus m, which is the auxiliary stack space that you're using. Okay, so you're given the string s and string t. Let's quickly write the private function. So it'll be like, okay, fine, int f, int I, int j. And we know one thing, if this string gets exhausted, we can return a 1. If the other string gets exhausted, we could not do the match. And if they are matching, which is this case, you basically try to return the f of, you match both of them, which is this, and you go across and you don't match, and that's what you do. And if that's not happening, then you go to the else. So if they're not matching, you automatically go to the else, so there's no need to write else. So f of, just decrease one, and that's what you will do. And you know, you have to you require both the strings, so probably you can carry both the strings as well. So kindly carry both the strings, and over here you can return f of n minus 1, m minus 1, s of t. And what is n? N you can call at s dot size, you can call m as t dot size, and that's what you can easily do. Let's quickly run this off and see if this is running fine. It is indeed giving us the correct answer. Time to memorize it. So just quickly call a vector int dp of n, vector int dp of m cross minus 1. And what you can do is you can just pass on the dp over here, just go across declaring the dp. And I've done this, and right over here as well, pass the dp over here as well, pass the dp over here as well, before returning dp of ij is equal to this. And you can say dp of ij is equal to this plus this. And yeah, one more state is, if dp of ij is not equal to minus 1, you can return dp of ij. Again, try to run this and see if this is running fine. It is indeed running. Let's quickly try to submit this off and see if this works fine or gives TLE, because it's the memoization code. As usual, it did give us the time limit exceeded. Why? Because we are using the memoization technique over here. We need to use the tabulation in order to remove this time limit exceeded. So let's go and check out the tabulation method. So as you saw, the memoization technique did give you time limit exceeded, right? So obviously we need to remove this auxiliary stack space and the recursion calls that we are making. And in order to do that, what we can do this is, we can definitely apply tabulation, right? What is the first rule of tabulation? Declare the same size of DP array. So just go across and declare the same size of DP array. Done. Then write down the base cases. So, and then write down the changing parameters in the opposite fashion. And then copy paste the recurrence. Is that what you do? Yes, that is what you do. So just write it across. So write down the base cases is what you have to do. But do you remember LCS, where we did something like one based indexing? In case you don't know, please follow the DP playlist. So over here, yes, over here, we are writing something as j lesser than 0 and I lesser than 0. So what we are doing basically is, we are as of now dealing with 0 based indexing. So there will be cases where a call for f of minus 1 will go, which means the string I is exhausted. The string is exhausted. There might be a call where there will be I and the j will be minus 1. That means the string j is exhausted. So we're moving to a negative index. So in order to deal with it, what we will do is, we will just add a plus 1 to everything that we are doing. We'll just add a plus 1 to everything we are doing. We were calling by n minus 1. What we will do is, we'll call it with n, we will call it with m. Okay. And over here, since we did a plus 1, now we know one thing for sure, this will not be lesser than equal to. Instead of this will be equal to, because instead of minus 1, since we did a plus 1, now a 0 will come. Instead of minus 1 in j, a 0 will come. So these two are converted. But one thing we know for sure, if we are dealing with n still means this guy. So that's one lesser. So over here, instead of this, you write s1 of I minus 1 equal to s2 of j minus 1. You just compare the previous guys. That's it. And I think apart from that, everything stays as it is. You carry on one based indexing, but when comparing, just make sure you compare with 0 based, because the strings are 0 based, right? And once you've done this, now you can easily write this off. So just go back into the code. Yeah, just go back into the code and just do these minor changes. Okay, so what I'll do is, I'll just do this minor changes. And just make sure you also declare the DP array of size 1 plus, because you've did this minor changes. And over here just do I minus 1 and a j minus 1. That's it. And apart from that, everything will stay as it is. And try to run this and you will see that this is definitely running fine. It is, but I'll not submit it because yeah, we know it will give TLE, so we are not going to submit it. Coming back to iPad, okay, write down the base cases. So what does the base case state? Let's come down to the base case. The base case states for everything, whenever j is equal to 0, you put a 1. And this is definitely going to be n plus 1 and m plus 1 now. So for everything where j is equal to 0, what does j equal to 0 means? No string s2. Because j0 means there is nothing left. There is nothing left. So I'll be like, okay, for every I equal to 0 till n minus, or rather n, dp of I and j is 0. For every j0, just put a 1. Any I that comes in, I don't care. Because as long as the j is 0, I'm gonna put a 1. Doesn't matter what I is coming. And what is the other case? I equal to 0. In this you have to put a 0. So that's going to be very simple. For any j, you're gonna say dp of 0, which is I, and for any j it is going to be 0. That's it. These are going to be your base cases. Just look at the base cases and try to write them. Perfect. So I've written the base cases. Step done. Next, write down the changing parameters. We definitely know the changing parameters are I and j. Where are the parameters changing? What did you do for I? From n to 0 is what you went. From m to 0 is what you went. What is tabulation? Tabulation is bottom up. You write the base case. Yes, you write the base case. So the base case has been written. Then you go to the next, then you go to the next, then you go to the next, and you get this answer. So you go to the next, which is from 1 to n. You go to the next from j, which is from 1 to m. And then you copy paste the recurrence in between. And the answer is at dp of nm, because that's what you call it. And if you do this, you indeed get your answer. So without actually waiting, let's get back and try to write this perfect tabulation code. So what did we do? If you remember well, we just made sure this is 0, nothing else. Let's write down the base cases. So the base case, if you remember well enough, it was for any I from 0 till n. Yes, you just go across and you put in 1. And for any j, which is from 0 till m, you're like, okay, dp of 0 and j is going to be 0. Perfect. And you know this is going to be from I equal to 1 till n I plus plus. And you know this is going to be from j equal to 1 till m j plus plus. And what you do is you just go back. Okay, let's take it. Copy paste the recurrence. These are the recurrence. Let's take it and copy paste. And yeah, probably we can just do some formatting. This looks fine. So you know, instead of return, this is what it will be. Perfect. Instead of f, you know, it's going to be dp of I minus 1 and j minus 1. There's no doubt in this. And this stuff will go off. Perfect. There'll be a plus. But this time it will be dp of I minus 1. And this will be j. Right? And then just take it off. Done. Now you know, in recursion, if this if was working, then this line would not have worked. So just make sure you write an else for sure. Because if it's matching fine, or else you just pick up this guy, which is dp of ij is equal to dp of I minus 1 and a j. And you say, okay, fine, you can go off. And right over here, you can say return dp of nm. And this is going to be your tabulation code. And now let's quickly try to run this. Okay, we got a wrong answer. Why did we get this? Let's quickly check it out. Okay, so why did we get a wrong answer? Because if you remember, for j equal to 0, you did put over here. But after that, you're rewriting. So just make sure the j actually starts from 1 instead of 0. Because for this base case, you can't rewrite the 0 that you've written. And now let's quickly try to run this. It does run. You can actually omit this as well. Why? Because you're already initializing everything with 0. So you can omit this as well. And now you can try to submit this. Okay, so we got a runtime error. It's mostly because of the integer overflow. Just make sure this has to be long. I'm not sure why, because I think that's a test case issue. But yeah, you can't do anything. So just make sure you just make everything as long. That's the best that you can do. And try to run this off. Okay, it does give the runtime error with these cases as well. Okay, so mostly it is getting an overflow again, mostly because of the conversion error or something like this. So generally what I tend to do is, let's convert this into double, and we'll convert this into double, and over here just do a typecast. That's what we can do. That's what I generally do in competitive programming. Okay, now let's try to submit this and see if this runs. Because that's how I will handle it. I was giving it long, but eventually it will overflow and you can't typecast it back. So what I did was I just made it a double and then we converted it back. In Java, this will not throw a runtime error. So can we optimize this? Yes, the space optimization technique that I've taught you from the last 32 lectures. You can. Why? Let's see. I minus 1. I minus 1. Again an I minus 1. Let's do a space optimization. So you'll be like, fine. I'll be like vector double. Yes. Previous. And you just have to keep the previous row. Why? Because you're just requiring the previous row's value. You don't require anything else. You just require the previous row's value. So what you can do is, you can just store the previous row's value. So just go across and say, okay, fine. Let's store the previous row's value. And similarly, let's define a curve which stores the previous row's value again. Okay, so what is this line doing? This line is basically going to every row. I means every row. It goes to row 0, row 1, row 2. And at every column 0, it goes across and putting 1. And since we're just dealing with 2 columns, if you see 2 guys, one is previous and the other one is the current that you will be computing. So what you can do is, in both of them, you can just put across a 1 at the 0th place, right? Let's go across and do this. Instead of this, you can say, okay, previous of 0 equal to curve of 0 is going to be 1. Amazing. Over here, this means definitely previous. Again, this means definitely previous. Again, this means definitely previous. And this means curve. This means curve. And once the entire row has been computed, entire row, you can actually switch it. And right here, you can say, okay, this is what you return, and try running this. It does run. Let's quickly submit this off. You'll see on the summation, it is also running fine. But how many arrays are we using? We're using something as 2 arrays, right? So let's analyze these couple of loops and try to see if we can reduce this into a single array optimization. So what am I writing? Let's go back to that. So in the array, what I'm writing is, sorry, in the loop, I'm writing I to this, j to this, and we are writing something as dp of ij is equal to dp of I minus 1. Very important. I minus 1, comma, or rather you can say, after doing the 2D space optimization, what you're using specifically is current of, that means the current row is what you're computing. At the jth column, you are saying previous of j minus 1 plus previous of j. You're using the previous row, right? This is on the first if, what you're doing. And on the else, you're saying curve of j is nothing but previous of j. That's what you're simply doing. Either you're using the previous guy, and so is there a use of the current while computing the curve? Basically, you had a previous, if I draw this well, you had this as previous, you had some values, and then when you came across to compute this, you computed this, yes, you computed this by using this. You computed this by using this or this. You computed this by using this. So either you compute like this or you compute like this. Will there be a problem? No. Why? Because you're using the previous guys in order to compute the curve. Let's understand. You're using the previous guys. You're using the previous guys in order to compute curve. So the first thing that I'll say is, okay, that means I can just do a slight shuttle change, and I can say if I run this from M to 1, it is still fine. Does that make sense? I'll be like, yeah, it does make sense and it is absolutely fine. Perfect. Now let's understand. So I've done this first change. Now let's understand. Again, come back. Now, how am I trying to compute? I'm trying to compute this. Okay. And after this has been computed, I am saying you be my previous, and there will be another curve that will come in. That's what I'm doing, right? And then again, I'll compute this using this, and then I'll compute this using this. That's what the procedure is, correct? But if I say that, okay, I'm not going to do this. I'm not going to use 2 because I'm using as of now one previous, one current. So let's understand, in order to compute this, what am I using? In order to compute this, I'm either saying if they're not matching, take the previous guy. That means whatever is here, just come across and write over here. Whatever is here, just come across and write over here. Which means this value is taken from this if this else is executed. Or if this if is executed, I'm saying j minus 1, which means this. Like that means if j is here, previous of j minus 1 and j, which means this. So j minus 1 and j. These two guys on addition gives you this guy. Correct? So can I say, instead of curve, even if I write previous of j, will that be an issue? Ask yourself. Something that we did in knapsack in 1D array space optimization. Will there be an issue? And the answer to that is, I don't think so there will be an issue. Why? Because once you've computed this, it basically replaces this portion. That's what you're doing. You're writing it on the previous itself. So whatever is computed here, it goes on writing over here. Next, when you try to compute this guy, you actually don't require this guy. So instead of creating another guy, writing it here, why don't you just rewrite here? Because we don't need this guy whenever we are computing this. Whenever we are computing this, we'll require this and this. This guy is of no use. So instead of storing here, I'll come and store here. That's what I'll do. And this is what we can actually write. So going back to the code, what I'll do is I'll do a slight change and I'll say, hey, listen, I'll do it from M to 1. So it's very important that it runs from M to 1 because we are replacing the guys that are no more needed. Like going back again to the iPad, you are actually replacing this guy because this is no more needed. If it have gone this way, you cannot replace this because in order to compute this, you will require this. And then once this is computed, you cannot put it here because in order to compute this, you require this. So you cannot go from here to here. It's very important to understand. Okay, so that's the first change that I'll do. Next, I'll just write previous and I'll take it off. Right? This is done. And this would have been previous j. Do I need to write else? No. Omit. So that's the one liner that I will straight away write. There is no other change. And I'll just remove this curve. Perfect. Again, I'll remove this curve. Perfect. And yeah, this should be my answer. Let's quickly try to run this off and see if this is running with 1 dp. It is. So you can look cool by just making it dp, like, you know, that cool stuff. dp looks cooler, isn't it? dp. Oh, that's a cool solution, isn't it? Cool lag raha na? And before this day, you were going into the discussion section and you're like, oh, what have they written? How have they written this? Now you understand, isn't it? In just in case you did understand, please make sure you like this video and tell me in the comment section, did you enjoy this lead code hard? This wasn't hard if you want to do it via memoization. This is hard if you want to do it this way because it does require entire concept to be clear. So I hope you enjoyed it. So guys, just to continue our tradition, tell me in the comment section for sure. And with this, I'll be wrapping up this video. Let's meet in the next one. Till then, bye bye, take care guys.